The last section of chapter 7, so let's label it as 7J. This is where we actually show you the applications, as in like word problems. Okay, so this is where you actually see what you have learned in chapter 7. How does that apply to a real life example? So there's a few types of word problems that is in the book. So this is in section 7.8 if you're referring to the book. Okay, and so let's go through the types that was discussed in these sections. So the first type that you'll be looking at is anything that's related with numbers. So let's take as an example, if 2/3, so this is all in writing, so you have to, in words, so you have to make sure you know how to read it. If 2/3 of a number is added to 1/2 of the same number, the result is 7. So your job is to find the number. Okay, so if you read the whole question, the whole story, it seems the only thing you're looking for is just one number. So you could call the number as x, for example. Okay, so let's start from the beginning. If 2/3 of a number, so 2/3 of a number, of just means multiply, so it's 2/3 x, is added to, so let's add this to 1/2 of the same number, so 1/2 of x, the result is 7. So you're told the result is 7. So direct translation of the words gives me that equation. So now your job is actually to figure out the equation. So as you can see, this is an equation that involves fractions. So what you've learned is to use the LCD, and in this case my LCD is 3 times 2, which is 6. Okay, so my LCD is 6, and I'm multiplying every single piece by 6. So 3 and 6 cancels to become a 2, and 2 times 2x is 4x. 2 into 6 is 3, so 3 times x is 3x, and that's 7 times 6, which is 42. So 7x is equals to 42, which tells me that x is equal to 6. Now, being a word problem, make sure you answer to the question, so the number is 6. Okay, so you answer to the question. And if you have time, you definitely want to try to check it. So 2/3 of a number, so 2/3 of 6 added to 1/2 of the same number, so 1/2 of 6. So you're told the result is 7. So let's check. 3 into 6 is 2, 2 times 2 is 4. Okay, 2 into 6 is 3, and then so it's plus 3, and true enough, the answer is 7. So it checks out. Okay, so let's try another example. So let's call this example 1, example 2. Okay, and this is another question that is in your book, so let's do it. It says 3 times the reciprocal. 3 times the reciprocal of a certain number subtracted from 2 times that number is 5, and your job is to find the number. Okay, so again, you are only asking for one unknown, so you can say, okay, let the number be x. Except now there's a little more to think about, so let's start. 3 times the reciprocal. Remember, reciprocal of a certain number, so if the number is x, reciprocal of a certain number is referring to 1 over x. Okay, so it just means numerator become denominator and vice versa. So 3 times the reciprocal, what it means is 3 times of 1 over x, subtracted from, watch out, subtracted from means this is in the back, subtracted from 2 times that number, so 2 times that number, and you're told the result is 5. So let's read again. You want 3 times the reciprocal, okay, but you want to subtract from, so subtract from as in you put it in the back, and 2 times that number. So this is what I need to remind you. A subtract from B really means B minus A. Okay, that was something we talked about. So let me just remind you again because of this word from. Okay, so you do have to reverse the order, which is what just happened here. Okay, so now my LCD is x, so I'm going to multiply everybody by x. The first term becomes 2x squared. This one, the x's cancel, leaving me with 3. And on the other side, I get 5x. So let me bring everything to one side because I need it to have a 0. The sum I'm looking for is -5, and the product I'm looking for is the front and back, which is -6. And that tells me I have to use -6 plus 1, so it's 2 and 1. So that tells me I have to use 2x and x. I need a -6, so that's -3 and a +1. Okay? And so 2x plus 1 makes it 0, tells me 2x is -1, which tells me x is -1/2, and x minus 3 is 0, tells me x is 3. So in this question, there is actually 2 possibilities. I have 2 possible answers. One is -1/2, or the other number is 3. So the number is -1/2 or 3. Okay, so there's 2 possibilities. Okay, so the solving portion of the word problem is really what we have just learned in 7.7. Okay, solving rational equations. And so the challenge for you in 7.8, which is the last section of chapter 7, is just to translate what the words mean in terms of equation. Okay, so that you're going to have to try a few yourself, and I've just shown you 2. Okay, and in your book there's actually 2 more for you to look at. And then it's your turn to work on some. Okay, so let's go on to the next type. Let's call this type 2. Okay, so the second type that you need to look at is something that involves distance, speed, time. So I guess I should just say distance, speed, and time problems. Sometimes we call them rate problems. Okay, so sometimes we just call them rate problems. Okay, so there is a formula that you need to memorize, okay, when you deal with distance, speed, and time. And I think most students find this to be helpful. D is S and T. So this little triangle that you see here kind of gives you all the different formulas. It tells you to find the distance is really speed times time. Okay, because if you want distance, all you have to do is cover the D, and you end up with S times T. Now, if you want to find S, then you cover the S. Okay, use your finger and cover the S, and what you end up with D over T. And if you want time, all you have to do is cover the time, cover the T, and you end up with D over S. Okay, so those are the variations of the formulas, and it all depends on what is given to you. Okay, so I think it might be best if you draw yourself a little table given the story. It kind of helps you figure things out. Okay, so let's try the example. I think we might have yeah, so let's try one example. Okay, so a boat moving downstream. A boat moving downstream with the current travels 250 miles in the same time that it can travel 200 miles against the current. If the current is 5 miles per hour, What is the speed of the boat in still water? So for you to understand how to do this problem, I think you need to understand some terminology. Assuming this is a river, okay, and you have water, okay, on the river, and supposedly the current is going in this direction, and you're told the current is 5 miles per hour, like that, okay, so 5 miles per hour, and it's going this way. Now, what it means is when the boat is in still water, that means without the assistance of the current. Okay, so if it's still water speed, so boat still water speed of boat. If you call this x miles per hour, that means, in other words, without the current pushing you either way, your speed is x. Okay, so there you are happily rowing the boat at x miles per hour. Now what happens is if you are going this direction, meaning you are going downstream, okay, and why am I saying it's downstream? Because you are going with the current. So you're going the same direction as the current, so that's called downstream. And so equivalently, it's like you are rowing at x miles per hour, but the current is pushing you, okay, so it's helping you. So in that sense, your speed becomes x plus 5. It's whatever you are performing, okay, and with the current pushing you, so it's like there's an additional hand. So that's why your speed becomes x plus 5. Now if you're going this direction, you notice this is called upstream. And why is it called upstream? It's because you are rowing against the current. So if you look at the current, it's going in this direction, okay, but you are going in the opposite direction. Then you're going against the current. Then equivalently, it's like you are happily rowing at x miles per hour, but the current is pushing you back, and is pushing you by 5 miles. So equivalently, your speed, your resultant speed, actually becomes x minus 5. Okay, so whatever your speed, and you minus 5 because the current is pushing you back. So in so many words, you better roll faster than 5 miles per hour, or your boat's not going to move. Okay, in fact, it's going to go backwards. Okay, so this is basically what upstream and downstream means. Okay, so for me to solve this problem, I'm going to draw myself a little chart. I have distance, I have speed, and I have time. So you are told that the boat moves downstream. So when it's downstream, your speed is x plus 5, and you are able to move 250 miles. Okay, so with that distance and that speed, to find time, you just take distance divided by speed. So it's 250 over x plus 5. And then you are told that if you were to travel upstream, as in against the current, you can only go 200 miles. So if you go upstream, your speed is x minus 5, but your distance will be less. Okay, so it's going to be 200 miles, so it's going to be 200x minus 5, and you are told that this time is the same. So the time used to travel 250 miles is equivalent to the time for 200 miles because of the difference in speed. So that's when they are telling you that these two are the same. Okay, so what we do in the setup is we equate those two together. So equivalently, we're asking you what's 250 over x plus 5 equate to 200 over x minus 5. That's because you are told they are the same time. Okay, so you equate the two times, and so now my LCD, if I'm looking at it, is x plus 5 and x minus 5. Okay, so I'm going to multiply x plus 5, x minus 5, same here, x plus 5, x minus 5. You notice x plus 5 cancels, leaving me with 250 times x, so it's 250x, minus 250 times 5, which is minus 1250. And x minus 5 cancels, so 200 times x, so I'm distributing, okay, that's what I'm doing here. So 200 times x is 200x, and 200 times 5 is going to be 1000. Okay, so now I'm going to solve. Now this time you notice the equation is linear. Linear meaning there's no x's. No exponents. So what you do is you separate the x's, x terms, okay, from the constants. So when it's no exponents involved, then I'm going to bring the x's one side. Okay, so I'm going to subtract that and bring the x's to this side, and then I'm going to add the 1250 to the other side, so that I end up with 2250, like that. Okay, so I want the x's and numbers to be separated, because the next thing I'm going to do is I'm going to divide by 50. So if you divide by 50, it will tell you x is, and that's when you can compute what 2250 over 50 is. And the answer came out to be 45. Okay, so remember what x represents here. We are talking about the still speed of the water, of the boat, still water speed of the boat. So speed of boat in still water, speed of boat in still water is 45 miles per hour. Okay. So let me give you a second example to look at, and let's try number 12 in your book. Number 12 on page 348. So, if you look at the question, it's talking about the distance between two stations. So, let me draw the picture since you all have your book. There's no need for me to rewrite the question. The distance between the two stations is 425 miles. Okay, so you are told there's two trains starting from different sides of the two stations. Okay, there's one station that's over here, and there's one station that's over there. And there's two trains, okay, and they are going to start simultaneously from these stations on parallel tracks and travel towards each other. So you have one train going this direction and one train going that direction. So the total distance is 425, and then you have train number 1 and train number 2. And what you're told is one of them is 5 miles per hour faster. So assuming this train is X miles per hour, and this one goes a little bit faster, and his speed is going to be X plus 5 miles per hour. Okay, let's try that. And they traveled for time travel is going to be 3 hours. And you're told that at the end of 3 hours, the distance between them is still 20 miles. So they didn't reach each other yet. So maybe after 3 hours, the first train is here and maybe the second train is here, okay? But the gap between them is down to 20 miles. Okay, so let's draw a little chart. You have distance, speed, and time. Okay, so I don't know the distance that they travel, but I know the speed for one train is x and another one is x plus 5. The time travel for both of them is 3. So if I know speed and time, then to find distance is speed times time, which is y is 3x and 3 times of x plus 5. So I know that for the distance wise, okay, one train is 3x plus 15 miles, and the other train is going to be 3x, okay? And so I know that if I add the other distances plus that 20, it becomes the total distance between the two stations. And there you have it, my equation. 3x plus 20 plus 3x plus 15. In case you're wondering where that comes from, that's really from here. 3x plus 5, so it's 3x plus 15, okay? And that total distance has to add up to 425. Okay, so what I have is 6x plus 35 is equals to 425. This is linear, so if it's linear, I will separate the numbers from the variables. So when I subtract 35, on this side is 390. So if I divide by 6 on both, it tells me x is 65. So speeds of the trains are 65 miles per hour. That's for one of them. And the faster train is 65 plus 5. So it's going to be 70 miles per hour. So that's the slower train and that's the faster train. Okay, so there is 2 types of problems that discussed in this lecture, and I will leave the other 2 for the second part. Okay, so you should look at part 2 for the 3rd type as well as the 4th type. Okay, let's get you to try some from these 2 types. So try, and let me give you the numbers. So for these 2 types, which is on numbers and rate, let's get you to work on, this is on page, it starts from page 347. Okay, so let's do numbers 1, 3, 5, 7. And those are the one on numbers. And for rate, as in distance, speed, and time, let's do numbers 11, 13, and 15.